Thanks for joining us once again as we look at some further work with vectors. And it's important within what we're doing to make sure that you're understanding the relationships rather than just memorizing formulas. So in the previous video, we discussed finding the angles at intersections between planes and finding the angles at intersections between a line and a plane. And now we're going to shift our focus to finding distances. So let's say we have a problem like you see in number 4 that we have point A, point B, and point C have given position vectors. So I'm just going to rewrite this as 1, 1, 2 for point A, and I have 1, 2, 3 for point B, and then I have 3, 1, 0, or actually, excuse me, not 3, 1, 0, 3, 0, 1 for point C, right? So here is A, here is B, here is C. A quick reminder that this is the X direction, J is the Y direction, and Z is the K direction. And so for 3I plus K, that's 3 in the X direction and 1 in the Z direction. Okay, so those are points, and they're in this plane P. We want to calculate the area of triangle ABC, right? So to calculate the area of triangle ABC, we can use 1/2 the magnitude of AB cross AC, right? That our vector product will get, the magnitude of our vector product will give you the area of a parallelogram formed between points A, B, and C, right? That if I kept this going out, right, the parallelogram that would be formed by A, B, and C. But uh, we only care about the area of the triangle, so that's going to be half of my area. So we need to figure out the directionality of AB. All right, so the directionality of A to B is going to be 0 in the X direction, 1 in the Y direction, 1 in the Z direction. And we need to figure out the directionality of A to C. That's 2 in the X direction, -1 in the Y direction, and -1 in the Z direction. And really and truly, I could have done BA to BC, or I could have done CA to CB. Doesn't really matter which directions I'm using, but I'm going to be setting up with two vectors because then I can play with the angle between the vectors, right? So I need the cross product. I'll go ahead and use my calculator since it's calculator active. And I'll come to my toolbox, come to my matrices and vectors, right? Vectors, I want the cross product. And if I go Shift E, that'll give me a row vector or a matrix approach. And so I have 0, 1, 1 for one of my vectors, right? Then shift to the bracket, 2, -1, -1 for the other row vector. And if I find that cross product, right, I know that that's going to give me, right, 1/2 times the magnitude of 0 to -2. And so that's going to be 1/2 times the square root of 0 plus 4 plus 4. Okay, so what does that mean? That means that the area of the triangle is equal to 1/2 the square root of 8, which is nothing more than the square root of 2. So, hence, how can I use that to find the shortest distance from C to AB? Well, let's draw in an altitude. And what do we know? We have another formula for the area of our triangle, right? That 1/2 the length of AB, right, times, right, my distance from C to A, that shortest distance, that has to be square root of 2 because the area of the triangle is the square root of 2. Now, what's the length from A to B? The length from A to B is nothing more than the magnitude of that directional vector from A to B. So that's going to be 1/2 square root of 0 plus 1 plus 1, right, times, right, the distance needs to be the square root of 2. And so that would indicate then that the distance is equal to 2. So that shortest distance is equal to 2. And the way we found it in this particular situation was working with an area of a triangle, right? And why did we work with the area of a triangle? Because it told us to, right? Hey, here's the area of the triangle. Can we make that connection that I have different approaches for finding the area of the triangle? Let's look at another question involving distances. Okay, so common things for distances is going to be the idea of having right angles. What's nice about having right angles is that we can find a distance in a variety of ways. If we have skew lines, we can figure out the shortest distance between two lines by using the vector projections, right? So let's say that I had, right, let me just draw this off to the side, right? Let's say that I had one skew line that direction, one skew line this direction, right? So they're not going in the same direction at all, but I do have some place that I'm going to be perpendicular to both of my lines, right? And so let's say that this here happens to be um, 0.2, right? And let's say that this over here happens to be 0.1. Well, I do have a relationship in going from 0.1 to 0.2 that makes a right triangle. With that right triangle, I can think of the normal to these two lines and say, hey, I have a relationship that goes with the angle for the normal. So really what I can do is say, I care about the part of P1 to between P1 and P2, the part of this directional line that is in the direction of this normal vector, right? And this formula is our basic formula to use to find the distance between two skew lines. There are other methods that can be used. However, understanding these vector projections and using dot products can help simplify the more difficult concepts later on. So let's have a closer look of how this is going to apply. So we want the shortest distance between two skew lines, right? Now, good practice would be to show they are skew, right? But within the context of this problem, right, let's say that we were told that we had skew lines. So if we weren't told they were skew lines, good practice would be to show they're skew lines. But let's say that we know that they're skew. Well, we care about our directional vectors primarily and about the points on our vectors. So line 1 is given by a x-coordinate of 8, a y-coordinate of -9, and a z-coordinate of 10, right? And has directionality 3, -16, 7. Okay. Vector 2, or line 2, has an x component of 15, a y point of 29, and a z point of 5, and then plus lambda, or not lambda, we already used lambda, so plus a parameter times, and I guess technically they're using t, so why not use t, plus t times 3, 8 in the y direction, and -5 in the z direction. So what I need to do is two things. I need to figure out to go from R1 to R2. I need to figure out that directionality. To go from R1 to R2, 8 to 15 is a change of 7. -9 to 29 is a change of 38. 10 to 5 is a change of -5. So that's my directionality. Okay, that's essentially right that P1 to P2. All right, so that's P1 to P2. Okay, I need the normal to the two vectors. So I need, right, 3, negative 16, 7 crossed with 3, 8, negative 5. That's going to be my normal vector. And then I can use this formula to find my shortest distance. So let's see how it works. Let's come to my calculator. I need to figure out a cross product. All right, and I'm going to do the cross product between 3, negative 16, and 7. All right, as well, and that's going to be crossed with 3, 8, and negative 5. If I find that cross product, that gives me 12 times 2, 3, 6, if I'm not mistaken. If we look at the scalar, if we look at the common, the greatest common factor of 24, 36, and 72, that's 12. So now I need to take that value, 12, 2, 3, 6, and I need to dot that with my directional vector of P1 to P2, which is 7, 38, and negative 5. If I find that dot product, right, if I find that dot product, that gives me 12 times 2 times 7, that's 14, 3 times 38, that's 114, 6 times negative 5, that's negative 30, right? And it's going to be all over the magnitude of the normal. What's the magnitude of the normal? That's going to be 12 times the square root of 4 plus 9 plus 36. Now, what is 4 plus 9 plus 36? That's equal to 49, so I have 12 over root 49. Now, notice that in this approach, very nicely, the 12 from the numerator and the 12 from the denominator will reduce to 1, and that is a property of using this particular formula. And so then I have 14 plus 114 minus 30, 98, and I'm going to divide it by the square root of 49, which happens to be 7, and so my distance is 14 units, right? But the shortest distance between these two lines is 14 units. But once again, how did that work? So I have one line, I have another line. These lines are skewed, okay? I have some place where there's going to be a perpendicular to the two lines. Well, how do I find a perpendicular to two different lines? That's where I use my cross product. That'll give me the perpendicular. Then if I call, like I said, this P2 and I have some P1 on my other line, I can look at the directionality P1 to P2. Okay. Well, what does this normal vector represent? This normal vector represents the projection of P1, P2, the projection of this vector onto the normal vector, right? And that projection is done by our dot product, right? That projection is done by our dot product, and that dot product then allows us to figure out this relationship. In a different video, we might discuss that in more detail, but for right now, do be aware that this approach with the dot product can help us find the shortest distance. Okay? Thank you very much for your time. Be sure to watch additional videos for how to work with distances.